hello. Here you're in the lab again. Yeah, come closer, come see. It's a little bit dark, so we can enjoy the electricity today. We're going to talk about lighting, but first I'm doing a little bit of wood art. So this is the art made with the wood. And we take and we use the different properties of electricity to conduct electricity, and it arcs like lightning sometimes, you see that, but we're trying to send it through the, sends it through the material using the path of least resistance. The electrons like to go, the electrons like to go between the point of the positive and the negative based on whatever path gives them the quickest route with the least resistance. And so once they get close together, they will arc, right? But if we put them far enough apart, they'll travel through the wood. And I have various things on the wood like graphite, which is in pencils, and baking soda. And we have a little bit of tang from our last time together. We're using the tang. And we're trying to see if we can make some interesting patterns here using electricity to burn it into the wood. Now there are wood burning kits you can buy for burning things into wood, but that's kind of cheating. I like to do it the science way. So we use the electricity. It's kind of fun. Try not to let the smoke out of the wires. And while we're talking about electricity, it's important for us to remember we are going to talk about lightning. Kind of looks like I'm drawing with lightning right now, actually. But as you can see, what we're doing here is very similar to lightning in that we can create these arcs of electricity, which are actually electrons which are flowing through almost like the atmosphere, if you will, to make a connection. So they're trying to connect, and that was an extreme example. So when we talk about the lightning, okay, we talk about electricity which is moving from the cloud to the ground. And the reason why, if you will bear with me while I get into this explanation, is because of the electrons. So the electrons are the little particles which they go around the atom. So they're an atomic particle. When they go around the atom, when they have a negative charge, and they can split off from the atom and they can go places, right? So when we break open a piece of electrical wire, like a piece of big aluminum wire, we were to take one and we were to kind of just like break it open, right? We were to take it apart and we look inside. Here, come closer, zoom in, come in. Walk yourself closer, get a good view. So inside here, when we look inside the wire, and I'm going to put on some lights now, maybe we can see a little bit better. Okay, hold on. See, put a little light on the subject. Woo, that is very, very enlightening. Okay, so when we look into the wire, we can see that it's full of electrons, right? They're spilling out all over the place. Now you might say, why is these electrons blue, right? There are all these blue electrons. Why are they so blue? I think it's because they're negative all the time. I mean, if you spend the whole time being negative, you're going to end up being a little bit blue eventually. Okay, so that's what I think. But I lost my marble container. Some people think I've lost my marbles, but right now it's just a container. But anyway, so we'll do this. We'll put them in the container. The container right there. Okay. So we know that the electrons are these small particles in the atom that go around the atom, and they can split off. And so the question is, why do the clouds make the lightning that comes down? I'm going to put on the light, so bear with me. Hold on. So the lightning comes down from the clouds, but where does it come from? Right? Like, is a lightning built up in the clouds already? It just comes out sometimes? Or how does this whole thing work? So here's what we're going to say. Electrons are easily excited particles, kind of like an average 5th grade boy. Very easily excitable, okay? So what they do is when the cloud is formed, it's little particles of water or ice in the atmosphere, and they're constantly moving and they bump into each other. And when they get bumped into it, they get kind of excited, right? They get agitated. And then enough of this happens that the whole cloud begins to kind of have these excess electrons, which are in this agitated state, all excited. These excited electrons are going around. And so the cloud kind of starts to pick up a charge, right? It has a positive end and a negative end. And typically, the negative end is toward the bottom. And as it's going across the ground, it's actually just that friction as the air moving over the ground can also add to this effect. And so you get these electrons, and they're being built up, and they're very excited. And then they get to some point, and all of a sudden, they find some place that's sticking up what has a positive. As a positive to negative, they go, whoop, and they connect like an arc, like lightning. So, these electrons are pretty good. Let me see, where did I get them? Candy, that's why. The ones that are blue, oh, hot. Ah! I think I broke a tooth. A tooth? Did I break a tooth? Let's see. Did I break a tooth? Oh, that's unfortunate. Oh, that's these glass marbles. I keep mixing up the glass ones and the ones that are candy. I have a sweet tooth. Well, half a sweet tooth anymore now. I used to have a whole sweet tooth. Now I just have a half sweet tooth. But I do like these. They're good. The candy. Chocolate, like a 6-lit. Yeah. Good. So, the clouds, they go along the ground. Bumpity, 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 bumpity. Everybody elbowing, getting excited and going, hey, you know, get out of my space, man. Like, can't I find some place to be myself? I just want to be me. And so the electrons, they get all excited. And then they make this bolt of lightning which comes down to the ground. Which, you know, arguably, you know, it's kind of a lot like when we bring our electricity together like this, we can kind of get the similar effect. When we get too close and it will jump, whoop, there it goes, just jumps straight across, right? It kind of cheats, takes the shortest path. Whoa, that's pretty exciting. Whoa, there you go. Okay, all right? And so we're getting a little bit of that effect of the lightning. See the strike there? I don't know if you can see that good. So, you know, what is it about this whole positive negative thing? So, you know, it's the opposites and they attract. And so the electrons, which have been agitated and excited, they go someplace where there's a positive charge, where there's a lack of electrons. So, and a lot of times that'll be the tallest object because the positive energy or the positive charge, that's the word, positive charge is kind of building up. And so the highest point is where typically it will want to go to connect. So, like if we see this, if I can show this, let me see if I can do this. So if I connect this to the board and I point them away from each other, okay, and I bring it together, okay, nothing really wants to happen, okay, but when it turns them toward each other, it gets a little bit more action, okay, and it's actually kind of interesting, but the more that they point toward each other, whoop, there we go, the more that they point toward each other, the easier it is to get that spark to go. Sometimes. I think the board may be a little bit dry now, so it's dried out. So, you know, what I did was I had the baking soda into water, and, you know, first, let me go back to safety for a moment. Let me remind you, okay, there's parts of this that are for you to do, and there's parts of this that are for me to do. So the part that I'm doing right now, this is for the part for me to do. I do not want to hear that any of my junior scientists out there went out and they started taking apart the household electric cords. It's like this one was no longer very flexible, so it was kind of done. But, you know, no digging up electrical cords from your father's garage and cutting it open. And, you know, no taking your sister's charger and taking it apart to mess with it. See, these things that plug into the wall, there's a lot of voltage and amperage there. It's very dangerous. So, you know, don't do that at home. Don't take apart things at home. And, you know, if I find out that, you know, Harrison or somebody else in the class has been taking apart the transformers from the motors, not the Transformers, the movies from the 90s and the 2000s or whatever, but the actual, like, you know, metal innards from motors and stuff like that. Don't be taking stuff apart. Just try to see if you can make an electromagnet, you know, wrapping stuff around steel and trying to lift heavy objects and stuff. Like, don't do that at home, okay? Leave that to professionals, okay? It's very dangerous. But, you know, when it comes to things that are like, you know, maybe with your parents' permission, there's things you can get a hold of that are a little bit more manageable because they're battery powered, so it's not quite as frightening for the parents. But again, we have to turn off the lights to show. But you know, come on closer. You have to see this. I think this is pretty cool. So I'm gonna shut off the lights again so you can see. So some of this here lightning that we're making at home. So this is battery powered. It's rechargeable. You can get it at, I think, Tractor Supply for $9.99 right now. Not that I'm advertising for them. I'm just saying that's where this one came from. You know, this is some slight modifications. You know, I can get it to do this, which, you know, may not look like much, but come closer. This is actually a plasma arc. And this effect right here, this is called, it's a ladder, right? It's called Jacob's ladder, which is, I think, reminds the inventor said, it reminded him of the biblical account of the angels ascending and descending on the ladder, right? So here, we're going to show it again, see if you can get that. And the reason that it's purple is, I don't know. I don't know if it's splitting off some hydrogen, perhaps, when it's making some coloration. But now we're going to see if we can modify this and see if we can get a little bit of zippy zappy. Sometimes I get a little bit carried away and I get to zap. Here we go. Can you see that real good? Again, that's a plasma arc. But you know, if I were to take something which was not conductive, which I think I have insulated pliers here, but if I was to take something that's insulated and I was to mess with this while it's running, see if I can grab it. It's teeny tiny. Okay, I get the arc started, but if I pull it apart, you see how it goes up. And so the reasons that it goes up is that the plasma is actually heating up the air around it, and so it's making it to rise because it's an updraft. And then it gets so far away, and it's like, oh, it's too far. And it loses the connection because the electrons that are in the air are being stripped away from the rest of the friends. And they're like, hey, I really didn't want to go nowhere, man. I wasn't that excited about this. You know, I'm not into this kind of whole lightning arc thing. But, you know, if they're close enough together, the excited electrons hit into them. They're like, oh, now I guess I'm excited and I got to go somewhere. So I'll go that way. So going back to my example as a wire, you know, okay, going back to this, you know, if you think about it, every electron has some place that it really wants to be. Where's my, here we go. Here we go. I had this example here. So if all the electrons had some place they really wanted to be, get some fresh electrons. Those were kind of tired. They weren't very excited. This is from a electron mosh pit. See? Getting the electrons excited. But the ones that were in the wire, before we mess with them, they're just sitting there minding their own business, and they're kind of in their own spots. So everybody kind of has a spot to be in spot. So if you can see that, all the electrons are kind of wanting to stay steady. But if you add a new one and you bump them, you can get them to go to a next spot over, right? So every electron is like, you know, what do you call it? The musical chairs. The change chairs, you just keep moving over. Or like when you're doing the decimals and you carry one, and you move the decimal place, 1, 2, 3, 4, over, you know, it's moving the decimal place. Yeah, the electrons, they just kind of move down the wire. So they trade places. But, you know, so we showed you, with the parents' permission, perhaps you can make an electrical one of these at home. Which, again, it's kind of, and it does zap you. Sometimes, I got to tell you, truth in advertising, sometimes it does get a hold of me. And it's not so much fun as you might imagine. But, you know, it's in the name of science. So, you know, it is what it is. Maybe they'll double my salary from 0 to like double O. Working my way to 007 eventually, I think. But so here we go. That is a true Jacob's ladder. I couldn't get it to do it, but you know, here we are. You know, God has blessed us yet again with just another wonderful part of His creation. Is the Jacob's ladder. Okay, right there. So that's, my father actually has a company, and this is part of his logo, Jacob's ladder. So, you know, I thought, well, that's fun. But, you know, what about the kids that work on the farm? You know, they have access to the cattle prods. Oh, now we can have some real fun. Okay? So, you know, we're going to see if we can make a Jacob's ladder on this one. Can you get a good shot of that? That's lightning right there. And now I'm going to take and make a minor adjustment, and we're going to see if we can, well, actually, I don't think I don't. Yeah, I think these pliers are better. Make a minor adjustment, see if we can get a better arc for you. Okay? Remember how I said the pointed wire kind of seems to help to amplify the effect? So here I have wires that have been pointed toward each other a little bit, so I'm going to make this as steady as I can. Oh, it's not quite close enough. It's a little bit persnickety, this thing. There we go. So if that's something you can see at home, so that is a representation of electricity in an arc form, which is essentially what lightning is. So lightning, we talked about, it's you know, quite powerful. I think it's something like 6 times hotter than the surface of the sun. And let's see, what else can I remember out of the top of my head? I think it was so lightning was only about 1 inch wide at its widest points. You know. And so the electricity, it's good for making the arc. You know, if you can kind of get the hang, it's a little bit of trickiness, but you know, if you can get it right, it really makes some spectacular art here with the zapping. Not a bad way to cook a hot dog either. But you know, electricity is involved in a lot of things. Whoops! I don't want to lose my cattle prod. That's not good. Let me put the safety on. Okay, all right. Put the safety on that. Put that away. We had, you know, let's take a moment to remember those who have fallen. Because so certainly were some casualties this time. We had some folks that didn't make it, you know. So there's the shortages and different things. But you know, we're talking about the things that only I should be doing. And in fact, with some of this stuff, there's actually special gloves that are rubber and leather And so when you get above a certain point with the voltages or the amperages, you need to really protect yourself. So, but you know, safety is a necessary thing. But here in the lab, we have controlled conditions. But you don't at home, so make sure that you don't be doing things at home that you know, gonna get you. It's not a bright idea. It's not a bright. It's, you know, like we said. Hold on. All right, and cue the joke. Here we go. All right, rolling. It's not a good idea. So it's not a bright idea to do these things at home without the proper safety. So, like for instance, knowing the voltage that the battery light bulbs work at is important. So you don't just go plugging things in because then they go boom, which is kind of fun if you're doing it on purpose and you have permission, but not if you're not used to it. So, you know, obviously I don't expect you to be doing these kind of things at home with a cattle prod and the homemade electricity, you know, lightning rod stuff here. But there are things that you can do at home, you know, because it turns out that some of you may have access to a voltmeter. So that's something fun with your battery operated toys to see kind of volts your batteries pull and check different things. But you know, that's kind of not everybody has access to that kind of material. So, but what I bet you can get a hold of pretty easily is mylar from the party stuff, party supplies, Dollar Tree, Walmart, places like that. You can get the balloons, you know, the balloons. And what you can do is the balloons. Now, you don't have to have the helium, it just kind of makes it more fun. But you take a balloon, right, and you see if you can get it to create a static charge, much like a cloud. So like this would be my example of a cloud here. One I would tape and I would just rub it with either the human hair or like a certain types of towels work effectively. You can try different things, work better than others. But you charge it up, okay, and so you let that go. And then you come over here and you take this balloon and you grab like maybe a fleece-lined coat, not a goat, but a coat. And you rub it inside of the coat, and then it gets a charge. Whoop, see that? How it pulls it over? Okay, so watch again. See if we can do it. We'll draw it over. Yeah, come on. Whoa, yeah, whoa, peekaboo, hello. So at home, what you can do, see the tree here? See how it's attracted? And I don't think you can see it over here so much, but the balloon doesn't have much effect on the plasma sphere over here. But the plasma sphere actually was attracted to metal. And so I can make a blender effect, which is kind of cool. Although it does kind of have a nails on a chalkboard kind of a sound. So, you know, don't do that unless you're trying to aggravate your sister, in which case don't do it. Okay, don't do it. But, you know, very annoying. But it can, it attracts the plasma within the ball, and it's trying to short itself out to the glass. But glass and ceramic make pretty good conductors. Pretty good insulators. So when you're doing experimentation at home, you can try to put something between and see if you still have an effect. So, you know, we just take more balloons. Like the water balloons are nice because they don't get too heavy. They're very smaller. And they just kind of, you know, you have baby ones and papa ones and mama ones. You just kind of, whoop, hey, come on. Whoop. Oh, come on. It's not gonna happen. All right, you know, and then if you go to the dollar store, you can get a hold of some of the Mylar tiny balloons. The tiny balloons, and try to see if you can do different experiments with that. And you know, Forky reminded me with Forky. Forky does science, you know. And Forky, he reminded me. He said, you know, we haven't played with styrofoam. Oh, Forky, let us take a moment for the fallen. Oh, poor Forky. But you know, Forky's gonna watch from a safe place over there. But you know, what you can do is you can go and you can get like the confetti. And you know, if you see this, there's a certain amount of it that's on and a certain amount that's off. Yeah, I think we can safely put these back on again. Make it a little easier to see. So this is a confetti balloon, has a confetti in it. Now if you take it and the jacket lining, which is kind of a fleece material, we take it and we kind of put it in there, and we scuffle it up, and we ruffle it up, and we do all that. And then you see how it's kind of, look at how it sticks. But if you take your fingers, you can kind of make your own kind of plasma ball with confetti. It can be pieces of tissue paper, small pieces of Mylar foil, these styrofoam balls, which are impossible to clean up. So, you know, maybe with your parents' permission before you go making the styrofoam balls, which are impossible to get up. But they work really good in the balloon. The trick is to put them in before you start to blow it in, because it's really hard to put it in after it's all full, when it's all blown up. So, you know, it's getting to be time to go. And my assistant's reminding me we had one more experiment, I think he was trying to tell me about. And it was the nightmare experiment. That's right, nightmare experiment, because it's really tough to keep cleaning it up. Okay, So take the boom out of a, all right. So this is a clear plastic tray. And we have a bunch of the little snowballs, the little tiny balls and things that were coming out of the styrofoam. Now we take it and we can see that the balls, they can be affected. And we take and we rub the wool. Wool is something to try if you have access to wool. Wool and synthetic fabrics, and you rub the balloon. And then you can take and you can try to see if you can influence in any way. And you see if I put my hand under there, I don't really get much reaction, but the balloon does. And that's because it has a charge which is affecting the charges of these smaller particles. They have, poles, positive and negative. And so if they're laying with the positive side down, and it's the positive side of the balloon, when they come close to each other, it goes flying away. So it's a static electricity. So the static electricity we can build up here with the balloon is essentially the same as what it takes to create the lightning. And the lightning is coming from the static electricity to a place near you, so please stay indoors. And I think that's all we have time for today. So, auf Wiedersehen, goodbye.